Hello everyone, thanks for watching this video. So you're welcome to another video where I'm going to explain how we obtain the Fourier coefficient Bn. If you remember, you will notice that we've been trying to build a foundation upon which we can understand the composition of a periodic function. So we've been trying to study how it's possible to break down periodic functions using only sine and cosine. So in this video now, we want to consider how to obtain the Fourier coefficient Bn in the expression that we are familiar with, which is f of x is equals to a naught plus summation n from 1 to infinity a n cos nx plus bn sin nx. So let's consider this. That expression I just mentioned to you is something we can break down to this. Like I said a naught, okay, then plus a1 cos x. If you consider all this, you can note that all this one we can express them as summation n from 1 to infinity a n cos nx. You can see that we have 1 here, we have 1 here, we have a2, we have 2x, we have a3, we have 3x, we have a n, we have cos nx. Okay, so likewise, like I've said, that summation from n equals to 1 to infinity bn sin nx, we can also express that thing too using this expression. You can see that you have b1 1x, b2 2x, b3 3x, bn sin nx, and I've explained the reason why we don't have b naught sin x. Okay, because sin 0 is 0, and anything times 0 we give it 0, so we don't have b naught, but we have a naught because cos 0 is will give us 1. Okay, if you remember when we are dealing with Fourier coefficient a n, the first thing we did was that we multiplied both sides of equation 6.1 with cos nx. And after multiplying both sides by cos nx, we evaluate the integral. We evaluate the definite integral from minus pi to pi. Then we now consider all the components, from the right hand side, one after the other, and we considered two cases. That is when cos n is equals to m and when n is not equals to m. So with those two things, we're able to achieve something. We're able to achieve the expression for an. So now we want to consider bn. So for this bn now, we multiply both sides by sin nx. Okay, we multiply both sides by sin nx, okay, and we evaluate the integral from minus pi to pi. So look at it now. We have sin nx multiplied there. This one here is the same thing as this. Okay, this one here we multiply this one by sin nx, then we evaluate the integral. So we do it for all of them. You can see it's very long. So, but one thing we are very sure is that if you can consider only this term that I highlighted here, it can give us the expression everything. And likewise, if you consider only, let me highlight it in green color. If you consider only this one, it can give us everything from here to here. We can still have integral minus pi to pi, b3 a3 cos 3x sin nx. So if you consider all these things, it's just like making it too general. So whatever we obtain for this one can give us all the rest. So we don't need to really expand the series anymore. So likewise, look at this integral to this definite integral. If you evaluate this one, it can tell us everything about the series of b1, b2, b3 times all these ones. So let's consider the issue now, okay? In a simpler form, we have this expression which we can still reduce to give us a simpler one, which is this, okay? So that is how we obtain 9.1. Look at this 9.1 very well now. You see now that we multiply f of x by sin nx, integral minus pi to pi, and this one we have a naught sin nx dx minus pi to pi, and this one we have cos ns sin nx, we have sin ns sin nx. Okay, let's start with the first one now. What is the first one? Equation 9.1. This is the first one. This is the first one. So we need to evaluate this integral. So we have this. So we integrate a naught is a constant. It can come outside. By the time you integrate sin nx, it will give you minus cos nx divided by n. Then you evaluate from minus pi to pi. So here we can now say that minus a naught n can come out here. Then we have minus can come outside, then we have cos nx from minus pi to pi. So we evaluate the definite integral to give us cos n pi minus cos minus n pi. So, but remember, cos nx, cos n pi is an even function. So being an even function, it means that this expression holds. What is the expression? Cos minus n pi is equal to cos n pi. Remember, even function, negative will disappear. So we start with negativity and it will give us positive. Okay, so we have this expression. So what are we going to do with this one is that we want to expand, we want to change this one. We're going to replace this expression. Let me highlight it in red because we don't really like red. Okay, let me use yellow, okay, so that we can see it. So this expression, this is the reason why we need to we need to evaluate the fact that cos minus n pi is equals to plus cos n pi. So we change this one to give us this expression. So that's why here you can see now that there's no negative inside cos n pi again. So if you look at this, cos n pi minus cos n pi will give you 0. So if you do that, it's 0 times this one will give you 0. So definitely the first expression in equation 9.1 will give us 0. So let's proceed to the next one. What is the next one? This is the next one. Let me highlight it. This is the next expression we want to evaluate now. Let me highlight it in yellow. This is the next expression now. So we have it on the screen now. Look at it now. This is the next expression. But remember, this expression here, this integral here, it has to do with the integer n and n here. So this integer will determine what we're going to get as the outcome of the definite integral. So because of this, let's consider two cases. The first case is when m is equals to n and when m is not equals to n. But remember, we've worked this before when we're dealing with equation 8.5 and 8.6. And if you remember this one very well, we've realized that either m is equals to n, either m is not equals to n, this expression will give us 0. Please go and check your lecture notes, equation 8.5 and equation 8.6. You see that we've derived this before. So don't let us waste our time on that. So you can check your lecture notes. So let's proceed. So that is the end of this one. This one will give us 0. We've talked about it. Even I can even explain to you. Let me give you insight. Remember that cos nx is an even function. Sin nx is an odd function. And when you multiply even and odd, what are you going to get? Remember that we've worked it out. And if you do that and you evaluate the integral, you will now notice the reason why this one will give us 0. Because we are multiplying even with odd. And do you remember what we're going to get? Remember I said even is plus, odd is negative, and plus times minus will definitely give you minus. And that will give us an odd function. And if this one is an odd function, remember the integral. If you partition it from minus pi to 0, then from 0 to pi, you now see that of minus pi to pi of an odd function will give you negative integral is 0 to pi of the same function. So that negative will cancel it, then you have is 0. So that's how, if you don't still get it, please go back to your lecture note and look at it. So go to equation 8.5 and 8.6, you will see this explanation very well. So the last time we want to consider now is this. So let me highlight it. This is the third term, 9.1. So let's proceed. This is the expression now. So how do we evaluate this one? Like I've said before, this constant nx and constant nx here, they are very important to us. So let's look at this equation 9.4. I believe you are familiar with 9.4. You are familiar with 9.5. So let us subtract. Why do I need to subtract? I need to subtract so that I can have these two expressions. What I need here, they are sin A and sin B. Those are the two things that are very important. So it is only if I should subtract that I can retain this sin A and sin B, sin A, sin B. So you subtract, because by the time you subtract, this one here will be subtracted from this and we give you 0, then it will remain this. So we have cos A minus B plus cos A minus B is equals to this. Okay, so excuse me, what I'm saying is this is minus. Thank you. So cos A minus B minus cos A plus B will give us this. Then this one again, thank you, is minus. So let's replace a with mx and let's replace b with nx. So we have this expression here. So looking at this, we can now obtain our expression for sine mx and nx. So that will give us 1/2 of this. So whenever we are dealing with this, we replace it with this expression. Please take note of the correction in your lecture note. So this is minus and this is minus. Okay, so let's consider the first case. That is when m is not equals to n. When m is not equals to n, so instead of us to evaluate this integral here, we can easily come back and deal with bn/2. Then this 1/2 will come here. Then we have, of course, nx, we have this. So you integrate this. If you integrate cos mx plus minus nx, then you have this expression. Let me highlight them one after the other. Okay, let me highlight them. This expression here, if you integrate, you have this one. And this one, if you integrate this one here, you will have this expression. So that is okay. So you evaluate from, you use upper interval, then minus, you use lower interval, then you have this expression. Then you recall the fact that sine minus n pi is an odd function, which will give us minus sine n pi. So you evaluate, look at it now, this expression here, let me use yellow, this expression here, and this one will give us, okay, so now that instead of minus pi, we now have ordinary pi here. And here too, instead of minus pi, then we have this one. Then you evaluate. Then one thing you can now notice is that this expression, we cancel this, while this one, we cancel this. Then you now see that this will give us 0. Okay, that is when b is not equals to n. Let's consider the second case. That is when m is equals to n. For this case here, we need to go back to our knowledge of trigonometry and come up with this expression again, which you are familiar with. So, but here, if m is equals to n, you see that we're going to have the same thing. Let's call it n. So this will give us sine square of nx. And sine square of nx will give us this expression. So here too, this and this, they are the same. If m and n, they are the same, then definitely this one will give us 0. If m and n, they are the same, this one will give us 2nx. So that's how we obtain cos 0 here and cos 2nx. Yeah, that's how we obtain them. Because if m and n, they are the same thing, if you subtract the same thing from the same thing, you get 0. So you have this. So from here, we can see that, and cos 0 is 1. Then we have minus cos 2x. So this one here, you divide it by 2, then you have this expression. So for this case, when m is equals to n, this is the expression we are going to use. So for m is equals to n, then we can now evaluate this integral to give us bn/2 integral minus pi to pi 1 minus cos 2nx dx. So if you integrate 1, you have x. If you integrate cos 2nx, you have sine 2nx divided by 2n. So you evaluate the integral, then you evaluate the upper bound, lower bound of the integral. Then you have this expression. Don't forget that x here will be pi, then minus 2nx become minus sine 2n pi. Minus sine 2n pi. So we have this expression here. Then minus, this minus here is talking about the upper separation. You know, you have upper band minus lower band. So this minus pi here, this second minus pi here, is to evaluate this. You know, x here, we turn to minus pi. Then minus 2n pi over 2n. Okay? So you have this expression, then you add it together, then you now see obtain our 9.8, because here we give us this one, this expression here, this expression we cancel this expression. So we have n plus n, we give us 2 pi, then bn times 2. So now that we are through with every part of equation 9.1, where's our 9.1? Let's go back. These are 9.1, we're through with everything now. So for this one, we've obtained 0. For this one, we obtain 0. For this expression, we obtain bn/2 multiplied by 2 pi, which is this. So from here, we can actually make our bn the subject of formula. Don't forget that 2 we cancel 2. So here we now have our bn to be this expression. So this is how to obtain the Fourier coefficient bn. As you can see, it's very simple. So we're going to go back to our online class. So please take your time to do tutorial 9.1. Very simple. You just need to evaluate this integral 1 over pi, then minus pi to pi, then instead of f of x, you change it to cos 10x then you do it, then you now see the beauty. So later on, we're going to continue this. Thank you very much for watching. Thank you. Bye.